Again to FlippedHarber for Calculus. In this video we're going to be talking about how to take the derivative of logarithms. Our objectives for this video are to learn how to apply the rule for taking the derivative of natural logarithms, how to learn how to apply the rule for taking the derivative of logarithms with a generic base, and then we're going to take a look at how to apply a technique of using natural logarithms to avoid using the product rule and the quotient rule. Our outline for this video will talk about what is the rule for taking the derivative of a natural log. Then we'll talk about the rule for taking the derivative of a log base a, or some base other than e, which is what the natural log is. Then we'll take a look at using these two logarithms with the chain rule, because the chain rule is such an important part of the derivative process. And then we'll take a look at how to use the natural log to avoid both the product rule and the quotient rule. And then we'll take a look at a more extreme example where we're actually going to avoid both the product rule and the quotient rule. Now, first of all, the derivative of a natural log, pretty easy rule. The derivative of a natural log of x is equal to 1 over x. To take the derivative of a log base b, that is where we have a base other than e, the base on the natural log. This could be a log base 10, log base 5, log base 2, log base anything we want, as long as it's a positive number not equal to 1. The derivative of log base b of x is equal to 1 over x natural log of b. So notice that natural log of b is in the bottom of the fraction with the x. The most common mistake I see students make is they multiply by this natural log of b rather than having it down there in the bottom of the fraction. So just remember it goes down there in the bottom. Now, if I wanted to, just give you an example of this, the derivative of the log base 2 of x, that's going to be equal to 1 over x natural log of 2. Again, that natural log of the base number is in the bottom of the fraction. If you don't see a base on a logarithm, that's the implied 10, log base 10. So the derivative of the log of x is 1 over x natural log of 10. Now let's take a look at a couple examples where we've got to use the chain rule here. I've got the derivative of the natural log of x squared minus 4x. So I know I have to use the chain rule because the stuff inside the natural log is something that's more complicated than an x. And over on the right I have the derivative of log base 5 of e to the x. So again, I know I'm going to have to use the chain rule because the stuff inside the logarithm is more complicated than just a plain old x. But I still start with my rule, 1 over, in this case, x squared minus 4x. 1 over the stuff that the natural log is operating on. And then the chain rule says multiply by the derivative of the inside. So the derivative of x squared minus 4x is 2x minus 4. So then I would just have a little bit of algebra to try to neaten this up. I'd put the 2x minus 4 on top, put the x squared minus 4x on the bottom. Now I could probably go ahead and try to cancel something with this, and you really should try to cancel, at least take a second and see if you could cancel anything with this. I could factor out a 2 from the top, I could factor out an x on the bottom. Nothing cancels, so I'm just going to leave it like that. Now when I take the derivative over on the right of that log base 5, I have 1 over what the log was operating on. So that e to the x on the bottom is just the quote-unquote inside from the logarithm times the natural log of 5, the natural log of the base number. Now this e to the x on the end is the derivative of the inside. The derivative of e to the x is e to the x. It is its own derivative. So the calculus here is all done. And it's pretty obvious what I can do algebra-wise. I can cancel the e to the x's because I have 1 on top and 1 on bottom. So the derivative ends up equaling 1 over the natural log of 5. Now, this seems a little bit odd. We have a derivative that actually equals a number. There's no x in here anymore. Well, sometimes that happens. It might be interesting to take a look at the graph for the log base 5 of e to the x and see what you get when you graph that. So that's up to you. I'll leave that to you guys. And let's move on to the topic of using the natural log to avoid the product rule. Now, you look at this and you're going, why is this in this section? There isn't even a natural log in here. Well, we're going to use the natural log. So my first step when I look at this and I want to avoid the product rule, why do I want to avoid it? I probably wouldn't with this one, but sometimes as things get bigger and hairier and nastier, I might go, wow, you know, the product rule is really going to make this a mess. You know, this is going to be a technique that I can use to avoid the product rule. And the first thing I want to do is take the natural log of both sides. So I have the natural log of y equals the natural log of the entire right side. Now, I use the natural log rather than a different log base because its derivative is easier. It doesn't have that extra stuff in the bottom of the fraction. So yes, we could use a different log base, but we don't because the derivative is easier. So I've got the natural log of both sides. I'm going to use a property of logarithms that is going to make this right side at least not a product. So I'm not taking the derivative right now. I'm just using some properties of logarithms that says when I take the log of two things multiplied together, I can take the log of them separately and add them up. So this is coming to us from Algebra 2 and pre-calculus. This is just a property of logarithms. And another property of logarithms has to do with this 2 right here, this power. This can come down in front of the natural log. So again, I haven't taken the derivative yet. I'm just using algebra rules right now. I get the natural log of y equals the 2, that squared comes down as a power, natural log of x plus 2, plus the natural log of 2x minus 3. Now, what I'm doing here is I'm avoiding the product rule. I'm swapping it out for an easy natural log rule and an addition rule. So now I'm not going to have to use the product rule when I take the derivative. So let's get ready to take the derivative of this, and I'm thinking, oh, I've got to do this implicitly because it's no longer solved for just y. So the first thing I do is take the derivative of the natural log of y. I get 1 over y dy over dx. So remember that this dy over dx is basically the derivative of the inside right here. And that shows up because of implicit differentiation. Now, my 2 right here is just the constant multiple 2. It's from this 2 in front of the natural log. This 2 over here is actually from the derivative of the inside. That 2 is the derivative of 2x minus 3. So here is my derivative, and I want to solve for dy over dx, so that means I'm going to multiply this y over to the right side of the equation. So I have dy over dx equals y times this entire right side. Now this would be a great place to stop if I was given a point, and by the way, the point for this original equation would be a good point, I should say. It would be the point 2 comma 16. I actually plugged 2 into the original equation and got 16 out. If they asked me to find a tangent line at a given point, I'd stop here. I'd go, okay, I know what y is. I'll just plug in 16 for y, and I'll plug in 2 wherever I see an x. And that would give me my slope. So I would then have the slope for my tangent line. So this would be a great place to stop with the algebra, with the derivative, and all that good stuff, if they asked me to find a tangent line at a particular point. But if they did not ask what's the tangent line at a particular point, if they asked me what is dy over dx, I'm going to need to go a little further. And what I'm going to do is I'm going to substitute in what my original y was equal to. So this stuff in the front is what y was originally equal to. Now I can multiply that into the parentheses and stuff will cancel. So if I multiply the x plus 2 squared in, the bottom of the first fraction will cancel. When I multiply the 2x minus 3 in, the bottom of the second fraction will cancel. And I can get rid of all my fractions. And I can even go a step further from right here. If I go ahead and FOIL things together, I can start to see that I have a lot of common terms that I can combine. I can combine the 4x squared with the 2x squared. I can combine the 2x and the 8x. So when all is said and done, this derivative is equal to 6x squared plus 10x minus 4. Okay, well, let's take a look at using this technique to avoid the quotient rule. So now I'm going to use my natural log to change that quotient, and in this case, when I take a quotient, if I take the natural log of both sides, my quotient turns into a minus. So it's the natural log of the top minus, and I brought my 2 down in front of the natural log of the bottom. So it's minus when it's a fraction. And now I take the derivative. 1 over y dy equals 1 over x plus 2 minus 2 over 2x minus 3. Now let's talk about these two 2's for a second. The first 2 right here is my constant multiple. My 2 that's on the top of the fraction is the derivative of the inside again. So you got to pay attention to that. What is inside the natural log? What's the derivative of that inside? Don't forget to apply the chain rule when you're doing this. Now, again, this would be a great place to stop if I was given a point and asked to find the tangent line. Since they would give me an x and a y value, I would plug in my x value, I'd plug in my y value, and I'd have my slope. To continue on, though, and find dy over dx, I'm going to substitute in what y was originally equal to, and I can even distribute this into those parentheses, and I can start to combine some terms. I can get 2x minus 3 squared is going to be on the bottom of my first fraction. The x plus 2 is canceled. I have a 2x minus 3 cubed in my second fraction. My x plus 2 doesn't cancel in my second fraction. If I wanted to combine these, I could create a common denominator of 2x minus 3 cubed, and I could even combine some like terms if I did that. But let's move on to take a look at some more extreme examples. So this is one where I've got the product rule on the top and I've got the quotient rule. So now if I use my trick, my natural log method, I'm going to take the natural log of both sides, and you'll notice that I've got my powers brought down. My squared came down in front, my cube came down in front, my cube came down in front, and I have the things that are on the top of the fraction are added minus whatever's on the bottom. So you'll notice, you'll notice that it's minus the 3 natural log of x squared minus 4. And now you can go ahead and see what my other steps are. I take the derivative, I get 1 over y dy over dx, and I just follow my chain rule along with my log rule, and I get these little fractions created. You'll notice the 2x minus 5 is on the bottom. The 2 that's on top is from the chain rule. X plus 5 is on the bottom of the second fraction. The derivative of the inside there is 1. So you just see a 1 on the top of that fraction. You see my x squared minus 4 on the bottom of that third fraction. The 2x on the top of the third fraction, again, is the derivative of the inside. Go through, just multiply your multipliers in front, your constant multiples in front. Multiply the y over. Again, great spot to stop if we've got to find the slope of the tangent line and they gave me my x and y point. But if I wanted to go even further, again, I would plug in what y is equal to. Now, for me, for the purposes of my class, I'm actually totally thrilled with this. I love this because this shows that you have learned how to take the derivative using this method. If you want to go into this further, you can multiply this big nasty fraction inside the parentheses. Some stuff will combine, some stuff will cancel, and you can actually move things closer and closer to one single fraction. But I'm not going to ask you to do that. What I really want you to demonstrate is that you can use this method to take the derivative. Okay, so that's it. That means it's time for you to try some of this stuff on your own. I'll see you in class, and I'll see you online.